right, back to integrals involving inverse trig functions. So in the last video, I kind of went through the proof of why this formula works. I won't do the same here, but we're just going to go ahead and do a couple of examples where we apply this stuff. So when are we going to use this? You're going to use this when you have a rational expression that has a denominator that is quadratic in nature, but you can't use a u substitution. So in each one of these cases here, you see that. Now, how do I know I can't use a u substitution? Because if I attempt a u substitution, like let's say let u equal the denominator, what I would need is I would need an x in the numerator in order to make that work. If there were an x in the numerator, my u substitution would work. I don't have that. And so when we have a situation where we essentially have a constant in the numerator and we have a quadratic in the denominator. Now, in these cases, what you see is I have a quadratic with a constant because that's what the format of inverse tan and inverse sine is. It's either a constant plus a squared term or a constant minus a squared term underneath the square root. So we have to be able to recognize that these look like an inverse tangent. All right, so the first one here is really straightforward because if I just pull a 3 out of the integral, I'm essentially already done because I know the antiderivative of 1 over 1 plus x squared is inverse tangent x plus c. So bam, we're done. Now, when I look at a problem like number 2, not as straightforward, but when I look at this, I recognize I cannot apply a u substitution because if I let u equal x squared plus 25, my du is going to have an x in it. I don't have that x. So if I can't do that, the next thing I notice is I do have x squared plus a constant. That is the format of an inverse tangent. Now we got two options here, and I kind of, well, I don't know if I mentioned in the last video or not. I can either do as I did in the last video where I proved this and factor out that leading constant there to turn this into a 1. In other words, I could factor a 25 out of the denominator. So that's one thing I could do. And if I do that, I'm going to turn it into this. Or I can just straight follow this formula right here. So it's kind of up to you. Do you want to remember this formula as well as this one and apply it? Or do you want to take this and turn it into that? I tend to do it this way just because it's one last thing for me to remember, but that's totally up to you. So I'll show you that method on this one. So what I would do here is my goal is going to be the following. First thing is to get the constant to be a 1 in both the numerator and the denominator, and then get the squared term here to be a perfect square. So I'll show you what I mean by that. So first step is I'm going to pull out a 7 and a 25 out of the integral. So 7 from the numerator, 25 from the denominator. When I do that, I'm going to have the following. So I've got my 1 there that I want. Now the next thing, as I mentioned, is I want to express that squared term of x squared over 25 as a perfect square. So x over 5 quantity squared. Now I'm going to do a u substitution, letting u equal x over 5. That will make my du equal to 1/5 of dx, or dx equal to 5 du. So now what's that going to do to my integral? I already have the 7/25 on the outside. I'm now going to have this 5 on the outside as well. And my integral is going to become 1 over u squared plus 1 du. And now what I've done is I've turned this into that. So this becomes 7/5 inverse tangent of u plus c, or 7/5 inverse tangent of x over 5 plus c. All right, now had I just used the formula up above, which I could have done. I could have just used that formula right there up above. What I would have done is I would have said, okay, in this instance, I'll just do it right here. My a is 5 because that's a squared. My u is x, right? And so that makes my du just equal to a dx. And so the antiderivative of this is therefore going to be the 7 I have in the numerator times 1 over a inverse tangent of u over a plus c. So I'd end up with 7/5 inverse tangent x over 5 plus c, which is the same thing I got right there. All right, and then let's just run through this last one real quick here. So I'm going to do the same method on this one. Again, I'm going to allow you, if you wish, you can use this formula right here, but I'm going to just do it this way. So once again, the first thing I want to do is turn that 16 into a 1. So I'm going to pull out, now a little bit different because when you pull a 16 out of a square root, it really comes out as a 4. Right, so I'm dividing out a 16, but the square root of 16 comes out of the integral as a 4. So this is going to be 1 over the square root of 1 minus x squared over 16 dx. I'm going to express the squared part of this as a single quantity squared. I'm going to do a u substitution, letting u equal x over 4. That makes du equal to 1/4 dx, or 4 du equal to dx. So my integral is going to become, I've got a 1/4 outside already. I'm going to add an extra 4 from right there. Integral 1 over square root 1 minus u squared. Crashing OneNote. Try that again. 1 over square root 1 minus u squared du. And now that's just your basic inverse sine antiderivative right there. So this will become, well, the 1/4 and the 4 are going to cancel out. It's going to become the inverse sine of u plus c, or the inverse sine of x over 4 plus c, like that.